Today we're going to continue our discussion of electrostatics. So as we continue, we have something called an electric field. And so kind of like gravity, when we discussed gravitational fields a little bit, we didn't really get into the deepness of them. But you probably have an idea of what a gravitational field is. Gravity exists over an area. It affects the further you get from Earth, the less gravity you have, but it still affects this entire space. Similarly, the electrostatic force is exerted over a field, okay? And so this means that objects don't have to be in contact to be in effect. And so the field strength, we just determined that the field strength at any point is determined as this equation here. The electric field E is going to be equal to the force, the electrostatic force, which we discussed last time, that kind of big equation, all divided by the charge we're talking about. So let's see an example real quick. Two oppositely charged parallel plates, 0.05 centimeters apart, exert a force of 5.24 times 10 to the negative 14 newtons on an electron placed between the plates. Calculate the magnitude of the electric field on the electron. So in this case, we actually have extraneous information in here. I put it in here just so we can figure out what we need. This distance is not part of the formula. Our formula is just force over the charge we're talking about. So in this case, our force is 5.24 times 10 to the negative 14 newtons. On the electron, which has a charge of negative 1.6 times 10 to the negative 19. So this is what we're going to do. Put this into a calculator. 5.24 times 10 to the negative 14 divided by, open parentheses, negative 1.6 times 10 to the negative 19. Close parentheses, enter, and I got negative 327, 500. This is, and the unit is just newtons per coulomb, just because it was a force is newtons, Q is in C, and so we just go ahead and divide the units themselves. Of course, we could rewrite this as negative 3.275 times 10 to the 5th Newton coulombs, if we wanted to. But this is fine too. So another part of electric fields is not just the equation. The equation's fairly simple. But the other side of it is that we need to be able to draw electric fields. We need to be able to kind of sketch what electric fields look like. Obviously, we can't actually see them with our eyes, but we can sketch the effect of our electric fields. There's 5 rules to drawing them, though. I'm going to discuss the rules, and then I'm going to tell you how to do them. 1, line should always point away from positive charges and always towards negative charges. So they should always follow the path that a positive charge would follow. Positive charges go away from other positive charges, and they are attracted to negative charges. The lines should never cross each other whenever you sketch them. Just don't have lines crossing. They should always intersect conductors at right angles. So if we have surfaces, we should always intersect at a right angle. Stronger fields are going to have closer lines, and so if we have bigger fields, we're going to show that by just having lines closer together. And then field strength and density decreases as you move away. So as we move away, the lines should be further apart from each other to show that we have a smaller density, smaller field. So what does this look like? We're going to do the one on the left. The left and right are separate here, so we're going to do 2 separate pictures. An electric field for just a single positive charge just looks like drawing field lines that point away from the positive charge. And so this is just a basic sketch of an electric field. So it shows that if we had some sort of point here, it would sort of go in this direction, right? If we had some positive charge, if we had some sort of negative charge, of course, it would go in the opposite direction, but we're only considering positive charges when we do our field sketches. Over here, since it's a negative charge, it's going to look the exact same, but the arrows are going to go into our negative charge, because a positive charge would be attracted to our negative charge. And from the sketch, we can see if we had a negative charge here, it would probably follow the path like that into the negative charge. Of course, it can get more complicated. If we have now these 2 charges are in the same area. So what does the field look like for both of these? Well, we have a line that goes out from the positive charge, and it's going to go all the way to the negative charge. And then this line, it's going to bend this way, or it's going to start out going this way, but as it gets further away, it starts to get attracted to the negative charge, and so it comes back. And so now when we have these other fields, we start getting this bending motion. So this is sort of what it looks like. There should have, the gizmos you did last time should have kind of demonstrated this. When you have the point charge that went through the field, you should have been able to see the path that follows, and that path would have been the field line, across that area. When you shot a positive charge, that is. There shouldn't be a line in the middle here. My bad. Assume the line in the middle is not here. I wanted to show one where they're both positive charges. If we have both positive charges, the other sides are essentially the same when you're on the outside. They're probably curved a little bit, but essentially the same. But as we go towards the middle, if I go directly this way, if I were to go directly this way, I would get pushed back. And so really we're going to show that as we go this way, we actually get pushed up from both sides because they're both pushing. And so imagine two equal forces pushing. They're going to kind of split as they get closer together. And so we get this sort of asymptote effect. If we had three charges, we can try this one. This one's going to be weirder. Let's see. I know here we're going to sort of have, if a positive charge here, it's going to want to go down because it's want to go to that negative charge, but it's got to it still gets pushed away from the charge to the right. So it sort of is going to make this sort of field. And then similarly, we're going to have this over here. And then we might have something similar on the outside of that. If we have a charge like this, something like that, and then the other way, they're going to get pushed away. The positive charges are going to be too strong, and it's not going to fully make it. And then over here, we'll get any sort of charge that's on this side will probably flow in. So we get something sort of like this. Maybe we get another charge there to fill in some of this other space. And so it takes a lot of practice. I would just look at videos, and we're going to do practice on the worksheet, of course, as well. There's some pictures on there. I want you to try sketching them. I would also just look at videos. They just take a lot of looking through them, messing with the gizmos we did last time, figuring out how fields work. We're always going away from positive charges towards negative charges. Of course, on the test, you're not actually going to sketch anything, but you should be able to identify fields. And, if I were to place a negative charge here, what would happen to it? Well, it's probably going to be attracted that way. So we have some more terms. Electrical potential difference. It has the capital V for its variable. The electrical potential difference is the work done per unit charge in moving a charge between 2 points in an electric field. So it's the energy it takes for a charge to move in an electric field from between 2 points. How much energy it takes for a particular charge. The unit is called a volt. You probably heard of this before. When we talk about voltage, that's the same thing, but we often refer to it as electrical potential difference. That's the full terminology, but voltage is the same thing. So if it takes 0.32 joules of work and moving a 1.7 times 10 to the negative 3 coulomb between 2 points, what is the potential difference between these 2 points? Well, we just follow the equation. It's the work done divided by the charge, so it's just 0.32. I should have put charge here. I think that was the typo. A coulomb charge. 1.7 times 10 to the negative 3. And then we can just go ahead and divide. 0.32 divided by 1.7 times 10 to the negative 3. Close the parentheses, we get 188 about volts. That's our answer. Parallel plates. If we have parallel plates, you can see this picture above. If we have parallel plates with the electrical potential difference between them, there's going to be a voltage that goes from one side to the other, and that's going to create this electric field that pushes electrons down. You can think about, if I had a positive charge here, it would be pushed away from the positive top plate and pushed downwards to the negative bottom plate through that force, and therefore there's an electric field in there. And because of the way this is set up, because each side has the same, force to it, it ends up that the force is constant over the entire plate. And so there's an equation for the electric field. The electric field equation is the voltage, is the potential difference between the two plates divided by the distance between the two plates. So this distance here, d. So let's say we have two parallel plates that are charged with a 110 voltage source and are separated by 0.5 meters. What is the magnitude of the electric field between them? It's, again, fairly simple. The electric field is the voltage divided by the distance between them. If our voltage is 110 volts and our separation is 0.5 meters, we just get 210. Or 220, I mean. 220. And remember our equation, or our units for electric field were Newton coulombs. We can also do a different unit called volts meters based off this, which is volts and meters. They're actually the same unit, they're just written differently. I tend to use Newton coulombs. So we'll stick with that, and that's what I'll use in all my worksheets and stuff as much as possible. But you should know the other one. Newton coulombs is the same thing as volts meters. Capacitors. Hold on one second. Capacitors are parallel plates separated by an insulator, okay? So no charge is actually going between them. They're going to be separated by an insulator. And because of that, they're actually going to store charge. They're these parallel plates that store this electric field between them, and they're storing charge, okay? Your phones are going to have them for different reasons, like whenever you use a flashlight on your phone or like on a camera, that's a very big voltage potential difference between them. It sends a lot of current out at one time. And so in order to do that, there's a capacitor in your phone that stores that charge, and so that charge can be released really quickly whenever you want to flash that light. And so that's an instance of a capacitor. They're used for different things. They're kind of like batteries, but they're not. Batteries are a bit different. Most batteries are going to use chemical or other things to give you charge. Anyways, but it stores charge kind of like a battery. It lets current flow whenever you want it. The amount of charge that can be stored for a capacitance, this term capacitance is the amount of charge stored for a given potential difference across the plate of capacitors. And so it has this equation here. Capacitance is equal to the amount of charge stored per volt, per potential difference. And the unit here is going to be farads, which is a capital F. And it turns out that there's an extra part to this equation. The capacitance is also determined by the area of the capacitor, so the area of the plates, the distance between the plates, and then this letter E, which is called permittivity. I'm actually forgetting I think it's an epsilon. Don't quote me on that. I think it's an epsilon. I'm forgetting my Greek letters here. But this little curvy E thing is the permittivity, and it's just it's because it's due to the material. Each material has a certain resistivity to allow an electric field. Not the material, the material between the plates, I should say, the insulator's resistivity. And so whatever material is in between the capacitors, it's going to have some sort of resistance to allow an electric field, and so we call that the permittivity. And so we can also find the capacitance by having this equation right here. Capacitance is also equal to permittivity times area divided by the distance. So let's try this out. Find the capacitance of two parallel plates of length 0.002 and width 0.003 that are separated by 7 times 10 to the negative 6 of air, which has a permittivity of 8.85 times 10 to the negative 12. So air is it's actually a pretty good insulator, it turns out. And so we can use air for our capacitance and for our capacitor. And so if we want to find the capacitance here, we can use this equation here. Our permittivity is 8.85 times 10 to the negative 12. Our area is length times width, so 0.02, my bad, times 0.03. And it's all divided by the distance between them. We're separated by this much of air. This should have been meters, my bad. 7 times 10 to the negative 6 meters. So we get 8.85 times 10 to the negative 12 times 0.002 times 0.003 divided by, and we need to open our parentheses when we do the division, 7 times 10 to the negative 6, close the parentheses, and I get 7.56 times 10 to the negative 12. And of course, this is the capacitance, so it's measured in farads. Couple more terms. We're going to go through them really fast. Current is the rate at which charge moves through a conductor, especially when we're talking about a circuit. This is how fast the charge is going through the circuit. It's measured in amps, and it's defined as a change in charge divided by time. So we can do that real quick. If we have 56 coulombs flowing through a 12 ohm resistor in 8 seconds, what is the current through the resistor? Well, I is equal to change in charge, the amount of charge flowing through, times divided by the time. We have 56 coulombs flowing through in 8 seconds. And so 56 divided by 8, of course, is 7. And so that's our answer. We don't care about the resistor, at least in this question. Resistance, we have this term called resistivity. It's a material's ability to resist electric charge, and it's measured in ohms, meters. And then we also have a term called resistance, which measures how the device reduces the electric current flow through it. And that's really what we're concerned with most of the time in a circuit. It's resistance. It's really just the pushback it has against current flow. It's measured in ohms, and it has this equation here. R equals rho times L divided by A, where rho is our resistivity. It's the material's resistivity. It has to do with the material itself. L is the length of our wire or whatever we're going through. So generally it's a wire, so it's the length of the wire. And A is the cross-sectional area. So it's actually like if you were to look down at the area of that wire, so like if that wire was a pipe, like how the diameter, like the area of that pipe. So let me maybe draw even a picture. If this is our wire, the end of the wire has a circle. We're just concerned with the area of that circle. That's what we're talking about here. So a certain wire is 4 meters long and has an area of 3.6 times 10 to the negative 6 meters squared and has a resistance of 0.075 ohms. What is the resistivity of the wire's material? So we have this equation, resistance equals rho length over area. And so we know the resistance is 0.075. We know that our resistivity is what we're looking for. Our length is 4 meters and our area is 3.6 times 10 to the negative 6. And so we can multiply this on both sides and then divide by 4. So 3.6 times 10 to the negative 6 times 0.075 divided by 4. And we get rho is equal to 6.75 times 10 to the negative 8. And of course, this is ohms, meters, as we discussed. And lastly, we have Ohm's law. This is probably the easiest equation. There's not much more to it. We know about voltage, we know about current, we know about resistance. And in any particular circuit, the current is equal to the voltage divided by the resistance. And this is what we're going to use a lot for circuits next time. And so pretty easy. If we have a 12-volt battery and we have 3 amps of current through it, let's find the resistance of that light bulb. Current equals V over R. And so our 3 amps is equal to 12 volts over R. Generally, if we have something on bottom, we want to get it on top. So let's multiply both sides by R first. And so we have 3R is equal to 12. So R, if we divide by 3 on both sides, is equal to 4 ohms. I went through that kind of fast. It's a lot of notes. You may need to slow down and go back through it a couple times. But really, the equations, we're not going to go super deep into them. You need to know how to do the math of them. You need to know what every single letter means. But I'm going to go ahead and give you things explicitly. It's not going to be as confusing as maybe some other equations we have this year, where you kind of have to dig and understand the equation. We're not going to go as deep. The equations are what they are. So you just need to know them, and you need to know what every letter is, and then you need to know how to use them. But they're not super deep, as maybe they have been in the past. Next time we'll talk about circuits. Circuits do get kind of tricky to an extent. And so if you haven't been doing the gizmos, it's okay. You should probably go through them because they really are beneficial. But the next classes, the gizmos, the circuits, both simple and parallel circuits and then complex circuits, it's very important you go through them because they're going to help you out a lot in solving circuits and figuring out how to do them, because circuits can be kind of tricky. Series generally is easy, and then we get to parallel, and it kind of throws your head through a loop a little bit, but then you figure it out, and then we get to advanced circuits, and people stumble really hard. And so, but the gizmos really does help out a lot, being able to actually play with the circuits and being able to see what they do and understand what voltage is, what current is, what resistance is. The gizmos actually does help out a lot here, definitely more than other gizmos in the past. And so I recommend doing it. But with that, you should be able to complete the assignment today. Email me or Canvas message me if you have any questions or if you need any of the keys. Have a good day.